Good morning, everyone. Thank you for joining us today. Sorry for the delay to start. Welcome to the next installment of the JKMRC Friday Seminar Series that takes place here in Indopili lecture theaters. My name is Karina, and myself and Katarina will be taking turns to introduce the speakers this year. We would like, on the behalf of the University of Queensland and the Sustainable Minerals Institute, we'd like to respectfully acknowledge the traditional owners and the custodianship of the land on which we meet today. We pay our respects to the ancestors and the descendants who continue cultural and spiritual connections to country. We recognize the value and contribution to Australian and global society. Our speaker today is Professor Gideon Rosenbaum, who is a structural geologist from the School of Earth and Environmental Science here at the University of Queensland. He is part of the Monash Mafia, having obtained his PhD from Monash in 2004. Gideon's research interests are in the fields of structural geology, global tectonics, addressing fundamental problems such as relative movements of tectonic plates, the nature of plate boundaries, and reconstruction of past plate tectonics process. He's particularly interested in the geodynamics of convergence plate margins and the controls of anomalous magmatism and ore formation. Today, Gideon will present on the spatial and geochemical anomalies in subduction zones and they link to ore depositors. Please help me to welcome Professor Gideon Rosenbaum.
Thank you very much. Thanks for inviting me to be here today. And we'll talk about spatial and geochemical anomalies in subduction zone. We can see here an example from Mount Etna, a photo that was taken a long time ago when I was still a master's student at the Hebrew University. And Mount Etna is a volcano that is spatially anomalous. It is positioned here in Sicily. It is positioned here in Sicily, and that is not the right place for an arc volcano. The trench is actually somewhere around here. So Mount Etna is essentially at the edge of the trench. The volcanic arc in this part of Italy, the Calabrian arc, the Aeolian arc is here. So Mount Etna is not in the right place, and it also does not have the right kind of composition for arc volcanism. Arc volcanism is typically calc-alkaline in composition. Mount Etna is more like a kind of a hybrid between a mantle plume and a subduction arc. So these are the kind of environments I will discuss today. But actually, what I'm doing here, it seems as if I'm doing really complicated kind of experiments here. What we're actually doing is preparing ashtrays. So just taking bits of lavas and kind of shape them as ashtrays, putting a little coin as a memento. So let's start with subduction 101. I believe that most of you, all of you know about subduction zones. We have an oceanic plate, or oceanic lithospheres are subductible material. So here are oceanic plates that subducting beneath the or beneath another oceanic plate, and the piece of lithosphere that is subducting is what we refer as the slab, the subducting slab. So I will mention this word a lot during the seminar. So we see here the slab subducting, and there is at the overriding plate above the subduction zone, there is a partial melting going on because of fluids released from the subducting plate. As the plate is subducting, mineral transformation leads to the release of fluids, and that can lead to partial melting at the overriding plate. And that is essentially the mechanism for arc volcanism, for arc magmatism. And that is also the factory for the development of ore deposits. Porphyry and epithermal ore deposits are developed in these magmatic systems, either directly from the magma or from the magmatic fluids. Now, the problem is that when we look at the distribution of ore deposits in subduction systems, in subduction arcs, we can see a lot of heterogeneities. There are clusters of ore deposits rather than being distributed kind of evenly in association with those subduction factories. We see clusters of ore deposits. Some areas show a huge amount of metals, like the area here in Chile and Peru. Other areas, in the Pacific Rim, for example, have much less metal. This is contained metal, contained copper, what we see here on the map. So there's a spatial heterogeneity. There is also temporal heterogeneity. I took this nice plot from a lecture that Stuart Smith gave a few months ago in the ore deposits hubs, and Stuart put together a lot of data from the Andes, showing clearly that there are episodes of metallogenic processes. There were, this is from Chile and Argentina. We can see that there were episodes where huge amount of contained metal was kind of fluxed into the system, and periods in between with very little development of ore deposits. There are also geochemical heterogeneities. If we look at the association, the geochemical associations of many ore deposits, we realize that they don't quite fit to the typical kind of textbook subduction magmas. Some of them do, but many of them don't. They show some sort of anomalous magmatism associated with the ore deposits. Here is an example of gold deposits in the Pacific Rim. And we can see that what Silito writes here, that approximately 20% of the large gold deposits accompany shoshonitic and alkaline suites. So these are not the typical kind of subduction arc magmas. In total, there would be about 3% of the volume in the Circum-Pacific. In reality, 20% of them actually are related to gold ore deposits. And in addition, there are structural heterogeneities. Many times you realize that there are some empirical links between structures in, of course, crustal structures, but also lithospheric structures, the structures of the geometry of the actual subducting slabs, like kinks in the downgoing slab that are somewhat connected to crustal structures, and that allows perhaps ascent of a high heat flow, and the metal-bearing volatiles are exsolves and forming ore deposits. So there are some structural connectivity as well. So let's look at the irregularities in subduction zones. And when we look again at the Pacific Rim, we can see that that there are many deviations from the textbook kind of examples. We see that many subduction zones involve subduction of crustal anomalies. Yeah, they are highlighted here in the dark areas, showing bathymetry, and hence the crustal anomalies. And we can see that there are seamounts that are being subducted, like the Emperor seamounts, the continuation of the Hawaii hotspot rock. There are oceanic plateaus, like the Ontong Java plateau, that arrives at a subduction zone. There are mid-ocean ridges that can arrive at subduction zone, like the Chile ridge that arrives here in Patagonia and essentially enters into the subduction zone. And obviously these things will have an effect on the dynamics of the subduction system. And perhaps in association with that, we realize that there are very complex subduction geometries. Just staring at the map, we can see that there are really kind of pronounced cusp, like the ones here, very close to where the emperor seamount is subducting. There's a very sharp cusp here. We see other similar geometries elsewhere, and there are stronger curvatures, like the Mariana, for example, here. And the other thing that we recognize is that there are pronounced volcanic gaps. So even though subduction zones should generate arc magmatism and volcanism, there are areas that subduction seems to go on, but volcanism is not occurring. So we'll talk in quite some detail about those gaps here in Peru and in Chile. We can see also in the oceanic ones here. For example, we see that there are kind of gaps in between clusters of volcanoes. So, what is controlling those gaps? So, what is the 3D response to the subduction of those crustal anomalies? And the response could be quite pronounced. Here are numerical simulations, 3D numerical simulations by Moresi and others, and they show subduction of pretty major crustal anomaly. This is like a piece of perhaps continental crust. So perhaps those bathymetric anomalies that we saw before will not have the same effect. But what we see here is that the subduction zone has the tendency of rolling back, simply from its own gravitational instability. So we see that the subduction zone is rolling back, and when the crustal anomaly arrives at the subduction zone, it essentially leads to reduced rates of rollback or even advance, or it basically affects the rollback mechanism, and therefore we get very strong bending of the whole plate boundary, and this bending can lead to tearing of the subducting slab. So really quite pronounced effects. We can see here a few examples from the Mediterranean. Here we see actual observations. This is based on seismic tomography in Italy. We are looking here to the northeast. This is the Italian peninsula, and we can see the slab, the subducting slab, basically being completely torn with a kind of a hole in the slab. And that was the result of this bending and rollback, basically just tearing the slab. Here we can see the same thing here schematically. This is the same kind of hole that we saw before, and that affects the whole kind of a flow around the slab. That's stenospheric, the mantle flow around the slabs. We can create kind of micro convection cells, and with flow that would be either horizontal, toroidal flow, or vertical, pollodial flow. We can see both flows here in the diagram from Facena and Becker. Here, toroidal flow perhaps will lead to even accelerating rollback, and pollodial flow, we can see it here. So we can create a very complex geometry of microconvection. And with a stenospheric material kind of upwelling, being able to upwelling through holes in the slab, we can actually create anomalous magmatism like Mount Etna. So here is Mount Etna. We can see here a hole in the slab here, and material, a stenospheric material can upwell and creating type of magmatism that is not dissimilar to mantle plume kind of magmatism, hence explaining the strain geochemistry. So from now on, I'm going to talk about South America for the rest of the presentation. And we'll look at the subduction anomalies in South America, the relationship to ore deposits and anomalous magmatism. So in South America, we see a pretty kind of a simple scenario of a subducting oceanic plate, the Nazca plate, subducting beneath the continental plate, South America plate. But there are clear anomalies in the subducting oceanic plate. We can see a pronounced anomaly here. It's called the Nazca ridge. So it's a kind of an oceanic plateau. Okay, essentially a thicker oceanic crust formed by perhaps a mantle plume. When it was formed, a mantle plume created an igneous province and a thicker crust. So there's the Nazca Ridge here. There's also a hotspot rock here, the Juan Fernandez Ridge. So these are the ones that I will mention. There are others as well. And perhaps related to that, we will explore this possibility soon, are the variations in the slab dip angle. So when the slab is subducting, it can subduct at a steep angle or at a shallow angle. But what we see in South America is that sometimes the slab is flattened completely, right? So here in Ecuador, we see maybe kind of pretty shallow, but still, 30 degrees subduction. But then we're moving to Peru to cross section B, and we see that the slab just becomes flat at 100-kilometer depth before it starts subducting again. We see the same in central Chile. So there are segments of flat subductions, and that perhaps explains why we get the gaps in volcanism. Yeah, the gaps in volcanism that very much coincides with the flat subduction. So very possibly the flat subduction is destroying the factory for the production of arc volcanoes. And we have ore deposits, as all of you know, we have a lot of ore deposits in the Andes. What we're going to do in more detail is exploring the area around the subduction of the Nazca Ridge in southern Peru. So here are the ore deposits in southern Peru. And, there is no, just looking at the map, there's no clear link between the distribution of ore deposits and the Nazca Ridge subduction, right? We see some very large copper deposits, gold deposits, and zinc deposits. We have very kind of a cluster of lots and lots of large zinc deposits. And if we look at contained metals, we start to see this kind of these pulses of metallogenesis that we already discussed earlier. We see that temporally, a lot of the metal was actually produced, particularly around 15 to 10 million years ago. So there is some episodicity here. And basically what we're going to test is whether there is a spatial temporal link between the Nazca Ridge subduction and the distribution of ore deposits. So what we need to do in order to do that, we need to look at the reconstruction. Okay, we need to reconstruct the subduction history of the Nazca Ridge. And here is the Nazca Ridge. And I mentioned before that it formed perhaps as a kind of a plume in something like Iceland, perhaps. Yeah, Iceland is positioned very close to a mid-ocean ridge, to an area of seafloor spreading, but there's an additional plume that just leads to a lot of magmatism in that area. So Iceland is not normal. There's a lot more magmatism than what you're supposed to have in mid-ocean ridge. And that was probably the case when the Nazca Ridge formed. And we can see that at about the same distance from the mid-ocean ridge, which is very far today, the East Pacific Rise, there is another oceanic plateau, the Tuamato Plateau. This is where French Polynesia here, just north of Tahiti. And you can see that they are kind of symmetric. They are like mirror image of each other. The difference is that the Tuamato Plateau is on the western side, the Nazca Ridge on the eastern side. One of them got subducted, the tip of it got subducted, and the other one has not experienced any subduction. Both of them formed in the East Pacific Rise and kind of migrated through time all the way to their present position. So that's really cool because we can reconstruct the shape of the Nazca Ridge before it got subducted. That's the bottom line. Yeah, if we want to reconstruct convergent plate boundaries, destructive plate boundaries, we need to know actually the dimensions of what been subducted. So here is the Tuamato Plateau, and that would be the Nazca Ridge, the kind of projected before it got subducted. And we can see that the whole portion of it actually got into the subduction zone. The other thing we can do is calculating plate movement. So we have the Nazca plate subducting relative to South America. So we can, if we know the movement of South America in a certain frame of reference, and we know the movement of the Pacific plate relative to if we know the Pacific relative to the Nazca, then we can work out the Nazca relative to South America. It's just a kind of plate circuits calculations. So we'll do that. And the other thing that we'll see in the reconstruction is an additional kind of plateau that Mark Gucher has described as the Inca plateau. You can see it here, completely subducted beneath Peru. And what Mark has suggested is that that was another kind of plateau that formed in the East Pacific Rise. It is found in the western side as the Marquesas Plateau. It got completely subducted in South America. And you can see that we have also the Iquique region, Austral plateaus, all of them kind of behaving the same. Okay, so let's look at the reconstruction. Here is the Peruvian coast 28 million years ago, and we can see that we have some ore deposits in the south, and we don't yet see the tip of the Nazca Ridge, but here it comes. Okay, so there are some ore deposits that clearly, are preceding the subduction of the Nazca Ridge. But when the Nazca Ridge arrives at the subduction zone, and here's the Inca Plateau further north, we can see that a lot is happening. So really nice kind of empirical relationship, the kind of 2 million year interval when collision should have occurred, when the Nazca Ridge should have arrived at the subduction zone, were associated with a lot of metallogenic processes at the overriding plate. And as we continue, because of the oblique plate kinematics, the Nazca Ridge is kind of sweeping southward along the coast of Peru. And you can see that more or less the ore deposits are migrating together with the Nazca Ridge subduction. Some of the timeframes look really cool. Some of them have more noise. But there seems to be some relationships. It definitely seems to make more sense than just looking at all the ore deposits in Peru without thinking about the time. So, so that is the reconstruction. And if we zoom out and look at the whole Andes, I haven't done these kind of experiments at the same resolution for other parts of the Andes, but what I did a long time ago is looking at the 10 largest copper deposits in South America and the gold deposits just from the USGS, and thinking, are those ore deposits kind of beyond Peru? Do they have any relationships to the ridge subduction? And in fact, even just looking at the map, we see some relationships. Yeah, we see that we have those that were already discussed in the Peru flat slab, and then we have many others here in more or less all of them in the Chile flat slab. But this is where the Juan Fernandez is being subducted. So I try to reconstruct the Juan Fernandez. We're looking first of all at the ore deposits, kind of the clusters of ore deposits. So we see, perhaps 4 clusters, and their kind of their timing. So the northern cluster is the oldest, from 14, 13 million years ago, and the youngest one is here in the south. So again, there is some sort of younging from north to south. And if we look at the Juan Fernandez is a hotspot rock, very much similar to the Hawaiian Perro, perhaps, that we see today in the Pacific. And similar to the Hawaiian Perro, it had a sharp bend. And this bend got already subducted, but we can kind of unsubduct the hotspot rock and see, with the same kind of plate kinematics that we did before, see how the Juan Fernandez is being subducted. And this is what we get. We see that 13 million years ago, the subduction of the Juan Fernandez was actually just opposite the northern domain. And again, it is migrating to the south, perhaps more abruptly because of the sharp bend. And we get this kind of southern younging from north to south. So again, perhaps the relationship, the spatial temporal relationships are of the ore deposits are linked with the subduction of anomalies. So we see those empirical relationships, and the question is, why does this occur? We can come up with many different explanations, but one thing that I'd like to explore, and that I have explored a little bit, is the relationship with the slab tearing. Yeah, so the anomalies are responsible for tearing the slab, like we saw in those numerical simulations, and that leads to anomalous magmatism, and that, you know, all these things are connected to ore deposits. So you know, whether the ridge subduction whether ridge subduction led to tearing in the Nazca ridge subduction, we don't we're not quite sure. There are numerical simulations here again by Hu and others showing that it could have led to tearing. You can see here the slab in blue, and it definitely seems to be, you know, a kind of torn and strongly affected by ridge subduction. There's some evidence that the Juan Fernandez ridge is that there is a kind of a tear in that area that we can recognize today in seismic tomography associated with the subduction of the Juan Fernandez ridge. But the question is, does so, you know, if tearing did occur, does it actually promote anomalous magmatism in ore deposits? And to answer this question, we need to actually ask ourselves, you know, what is anomalous magmatism? Yeah, we refer to that as a SJAM, spatially and geochemically anomalous arc magmatism. So what actually, how do we define? We go to a place, how we actually know that this is anomalous and that is normal? So we're going to spend some time looking at that question. And in correspondence, once we understand what is anomalous, what actually is the 3D geometry of the slab? Yes, so the present day slab in South America. So we're going to concentrate on the present day. So not the Marsen kind of reconstruction of the Nazca ridge subduction, but the present day situation in South America, relationship between anomalous magmatism and the slab kind of disruptions. And to do that, we looked at the Holocene volcanoes in South America. So volcanoes that are youngest than 10,000 years. And I just took the database from the Global Volcanism Program, and I also looked at a slab model. So a compilation of seismic data and seismic tomography, and you know, any kind of thing that can constrain the slab geometry from Haynes et al. And that gives us essentially a kind of continuous surface of the slab. So that is that's what we see here. We can see now those areas of flat subductions very clearly by looking at the distance between the slab contours. So we recognize we can see the volcanoes, 165 volcanoes, 3 major clusters, as we already saw before, in the areas of flat subduction. And if we look now in kind of more carefully at spatial relationship between volcanoes and the slab structure, we start to see spatial anomalies, right? So, you know, typically the volcanoes will be situated perhaps 100 kilometer or 120 kilometer above the slab, but there are volcanoes that the slab is much deeper below. Typically, the volcanoes will be along a slab contour, so kind of parallel to the trench, parallel to the slab contours. But there are areas like here in Ecuador where we see that we have one volcano after the other, and they're actually going along the deep of the slab, yeah, from those volcanoes here all the way to Sumaco, which is really much deeper. Yeah, we can see also in other gaps that we didn't quite recognize before, you know, just by zooming in. There's a gap here in Colombia, you know, what is controlling this gap? Yeah, moving to the central Andes, we can see here, you know, a volcano that is entirely in the wrong place, right? It is very close to the edge. Yeah, it is at the edge of the flat subduction. So perhaps that explains why it is there. We can see here in the center of the Central Andes, again, some gaps. So clusters of volcanoes, gaps, and a couple of volcanoes that they are way, the slab is way too deep below. And here in the southern part of the Central Andes, really kind of curious shape of the arc, showing really tight bending of the volcanic arc. One volcano here that is the slab is too deep below. So really interesting spatial anomalies. Looking at the southern Andes, again we see a couple of bends, less pronounced than in the Central Andes. We can see one volcanic field here that is kind of beyond the slab, so maybe at the slab edge. So there's actually, according to the slab model, there is no slab below, and 3 other volcanoes that are situated in the back arc. The slab is really very deep below. Okay, so all these are spatial kind of anomalies, and the question is, why do we get magmatism there? Why volcanism occurs there? And I can think about two explanations. One of them, that the mechanisms of melting is different than the textbook examples that we saw before. Yeah, it's not the right position, obviously. Another alternative that we need to keep in mind is that the slab model is not correct, because everything we do here is relative to the slab model, but the slab model is just a model, and maybe it's not quite accurate. And I will try to demonstrate, at least with one example, that the reality is probably a combination of both. There are inaccuracies in the slab model, and the melting mechanism is different. So let's look at just a number of kind of relationships between the subduction parameters and the different volcanoes. And we can see here the densities, so emphasizing the gaps, also the Columbia gap here in the north. So just a cross-section kind of going from north to south along the Andes, the distance along the Andes. We can see the crustal thickness below each volcano. We can see the obliquity of the subduction. So we can see, for example, that here close to the Columbia gap, keep losing the mouse. Close to the Columbia gap, we can see that the obliquity is very high. So maybe controlling the Columbia gap, and the convergence velocity is very low. So maybe that's the reason why we get a gap in the area of close to Nevado de Huila in Colombia. The age of the subduction of the subducting lithosphere, the slab depth, we already discussed that. So we see those like clear anomalies, really, sometimes more than 200 kilometer depth of the slab below a volcano, and also the slab deep angle beneath each volcano, simply calculated from the slab model. So the next question that we ask is whether those spatial anomalies are also geochemically anomalous, and that is a way more complicated, obviously. So we took data from mainly from GeoRock, and ended up with almost 5,000 major and trace element analysis. The number of volcanoes reduced to 124 because some volcanoes do not have any data. And we put everything together and try to think, what does it tell us about the kind of textbook example versus, something that is not quite right. And this is just the silica versus alkali for the different segments of the Andes, and immediately we see something interesting. Typical arc volcanoes should be calc-alkaline in composition, so they are supposed to be where we get the major cluster, right, around here. And we can see here that Sumaco particularly, maybe, and Sumaco in particular, is quite mafic in composition, quite low in silica, but very, very high in alkalinity. So these are those shoshonites that we mentioned before. They're the ones that are very commonly associated with gold deposits. And when we look at the Central Andes, we see that we get less kind of geochemical anomalies, and perhaps part of the reason is that the crust is very thick, and we don't the magmas just get kind of fractionated as it makes its way up, so more difficult to find anomalies. And in the southern Andes, we see again, a lot of alkaline volcanics, particularly in Payún Matru, in crater basalt. These are those spatially anomalous volcanoes that we saw before. But we need to do something more. I mean, just looking at the alkalinity is not really enough. So we decided to come up with a kind of a set of criteria to define anomalous arcs. And to do that, we excluded all those magmas that are high in silica and low in magnesium, and also those that have too much magnesium because they are likely just representing cumulates. So we see here in blue those more primitive magmas, and in red the more fractionated ones that basically tell us a lot about the crust that the magma is percolated through, but not on the original melting of melting mechanism. So we end up with a lot less analysis, obviously, by kind of screening all the data. And then we start to consider, different criteria. So the role of slab fluid metastomatism. Slab fluid metastomatism is the primary role for magmatism in arcs, right? So we tend to get a lot of elements, that are fluid mobile, like barium. Yeah, so they will be enriched in arc magmas. Yeah, we'll have in kind of normal arc magmas, we'll have depletion of fluid immobile high field strength elements. So we can come up with those kind of proxies for, if we deviate from those relationships, then there's something anomalous. Okay, we can look at all the data again, just the distance from north to south, and see, all the blacks are those that are kind of less normal. And we can see that there are kind of areas that are less normal, like in the northern Andes around Sumaco, and many places in the southern Andes, in fact. Then we can consider the degree and depth of melting and the slab melt. So looking at the alkalinity, we just talked about that. So in arc magmas, we have a pretty large degree of melting, and therefore low alkalinity. Lower degree of melting means lower alkalinity. So incompatible elements are enriched if melting is low. We can look at the slab melt input. So a high field strength element can be mobilized by slab melt. So higher values when we have slab melt. And we can look at perhaps the depth of melting. So if we have a residual garnet, we get higher values of lanthanum to ytterbium proxy. So again, we look here at a long strike, and we find again around the area of the latitude of Sumaco, we get this kind of anomalous behavior. And now in the southern Andes, actually we have only one zone that is kind of anomalous according to this criteria. And finally, we can look at the role of sediment input. In normal subduction, we expect to bring sediments into the subduction zone, and thorium is enriched because of sediments. So we can use those proxies for defining normal versus anomalous subduction. So again, we do the same here. So altogether, we end up with different criteria. Yeah, if a certain volcano does not, there's not a single analysis that actually passed the first filter, we give it a score of 0, and then we give 1 score for each kind of anomalous criterion. So a score between 1 and 8 for anomalous. The most anomalous volcanoes will get a score of 8. And putting all that together on the map, we can see now the kind of scoring for the different volcanoes. And Sumaco, already mentioned Sumaco a few times, gives us a score of 7. None of the volcanoes gave us a score of 8, but clearly Sumaco is geochemically anomalous. And in the central Andes, we see that most of the data did not pass the test, the first filters. There are a lot of volcanoes here in black for which we have no data at all. So the central Andes is much less kind of telling. And in the southern Andes, we get the crater basalt and Payon Matru, those in the back arc. They are clearly anomalous. Yeah, Laguna Blanco as well, the one in orange. And the next thing that we're going to do is to ask ourselves, are those anomalous volcanoes, so Sumaco, for example, are they actually linked to some heterogeneities in the slab? So it got a score of 7, clearly anomalous, and it's an interesting position. We saw that already before. It's far from the trench. We can see here the Google Earth image of the arc in Ecuador. We can see that we have a kind of a frontal arc. In yellow, we have the main arc, and in the back arc, we have only 2 volcanoes, Sumaco and El Reventador. And Sumaco is way out. It's already, you can see it's already in the forest, in the kind of almost in the Amazon forest, not in the high kind of summits of the Ecuadorian arc. And it's also positioned kind of opposite to the area of ridge subduction. We didn't talk about this ridge, but we can see here that there's another ridge here, the Carnegie ridge subduction. And there's also a fracture zone, the Grijalva fracture zone that is being subducting here opposite Sumaco. And it's close to the edge of the flat subduction. So the Peru flat subduction, we can see the slab contours here, is kind of the bend in the contours is very close to where Sumaco is. So we looked in more detail at what actually happening to the slab in that area of northern Peru and southern Ecuador. And to do that, we compared the slab model to observations. These observations are from the ISC-EHB catalog for earthquakes. We took intermediate earthquakes, and those earthquakes are considered to be slab earthquakes. Yeah, when you get earthquakes at that depth in this kind of environment, they are produced at the top part, top kind of 10 kilometer of the slab when it is subducted. And you can see that there's a lot of seismicity in the area of the flat slab, like really, really seismically active area. Many of them are about 100 kilometer depth. That is where the slab is flattening. There is an area here of really, quite deeper earthquakes up to 300 kilometer and, clustering all together. This is the El Puyo seismic cluster. We get much fewer earthquakes further north, but they are, we find them here and there. And but there's a whole gap north of, in the area of Sumaco, north of El Puyo seismic cluster, there's a whole gap in seismicity. So what is going on here? We really don't know. If we don't produce earthquakes, we can't visualize what the slab is doing. Okay, but there's a really sharp kind of change from seismically active, very seismically active area to a gap. So another thing we can do with the earthquakes is looking at the tension direction. The earthquakes give us indications on which orientations is the tension direction, which direction is the pressure direction. And those areas of those vectors of tension are essentially giving us information on the slab, on the movement of the slab in the subduction direction. So we can see that in the area of the flat slab, it has certain kind of plunge and plunge angle. Yes, so they are very flat kind of vectors here in the flat slab area because the slab is flat. And in the El Puyo seismic cluster, they start to plunge in higher angles, and they also rotate. Yes, so we kind of move into a different orientation. So the slab is kind of taking a bend and rotating in that direction. So really interesting. Okay, we can look at the cross sections. So just kind of taking cross sections of all the data together. So this is in the north, and reconstruct the slab. So 30 degrees, like we saw before. And in the south, the flat slab, yeah, a lot of seismicity, so really robust kind of reconstruction of the slab geometry. And we can see that the slab model is shown in those lines that we see here, is consistent with observations. But when we look at a cross section from north to south, so this is quite unusual kind of cross section. It's not parallel. It's not parallel to the subduction direction. It's perpendicular to the subduction direction. We can see really interesting thing. We can see the area of flat subduction here in the south, the El Puyo cluster here, seismic cluster here, the gap, and this is the area of normal subduction in the north. And these are the kind of contours of the slab 2 model, of the slab model. And you can see that they are not consistent. They are actually earthquakes. They are observations that are much deeper than the slab model and observations that are shallower than the slab model right here. So we think that this is where the slab model is actually inaccurate, because the slab model assumes that the slab is continuous. And in fact, what we might have here is a tear in the slab. Right? So we think that another way of looking at that is just comparing the seismicity with the depth of seismicity with the depth of observation, or with the depth that we get from the slab model. And we see that the El Puyo seismic clusters are all too deep. In red, here we have all bunch of earthquakes that are too shallow compared to the slab model. And essentially, we interpret the kind of the transition with the seismic gap as a tear. Right? So we think that essentially there is a tear in the slab in that part. This is where the slab model is inaccurate. And that tear is the tear that's responsible for a stenospheric material to kind of bring material from below and responsible for melting in Sumaco, so some sort of collodial flow, perhaps a kind of a trapdoor mechanism, yeah, while the flat slab is being created. So, you know, this is schematic kind of illustration of how you can form this tear. You create a flat slab perhaps by ridge subduction, and the opening of the tear is in a kind of a trapdoor style. Okay, so we see kind of relationship between the high score in Sumaco, high score anomalies in Sumaco, you know, spatially anomalous, and a real disruption in the slab. So I think I start to run out of time. If we want to leave time for questions, so I will not spend too much time talking about the other segments. We haven't done this level of work for the other parts of the Andes, but I mean, there are relationships between those spatially and geochemical anomalies to a possible disruption in the slabs. You know, just taking from others people work, there's a possible tear, much deeper tear in that part of the southern Andes. And you know, that perhaps the kind of scenario that we have in mind. So the slab edge, the tear, are those that allow a stenospheric upwelling and production of those volcanoes. And in the central Andes, we really don't know, because the data, the geochemical data, is so poor. I mean, it's so fractionated that we can't really, we don't really know what exactly is anomalous. We do see those gaps, you know, in this segmentation and bending, and you know, perhaps this is just a hypothesis. Perhaps there is some relationship between the anomalies. We need to prove that they are anomalies indeed, and the kind of curvature of the slab. Yeah, all this area has the boundary itself, the subduction boundary is curved, and that can cause slab disruptions, you know, in the same way that Rob Holmes and Simon Richard described for New Britain. Yeah, kind of a curvature in the slab that creates a tear here, and this tear, by the way, is just below Lihir in Papua New Guinea. So perhaps, you know, the same kind of curvature in the central Andes is responsible for those disruptions. But as I say, I really start just waving my arms here with speculations. So to conclude, large porphyry epithermal deposits are empirically linked to anomalous subduction processes like ridge subduction and the slab tearing. All these things are kind of interlinked. In a present-day modern arc setting, the Andes, the spatially and geochemical geochemically anomalous arc magmas correspond to areas of slab tearing and slab edge. We're able to see that. We had the scoring system that we developed based on geochemical indices, and we saw that it provides a powerful tool for recognizing anomalous arc magmas. And if we're able to recognize those anomalous magmatism, then we might be able to use that in the geological record to reconstruct the history of subduction zones and informing us on preferred locations for ore deposits in arc magmas. Thanks a lot.
Thank you very much, Professor Gideon. Very informative. Thanks for sharing your knowledge.
Thank you.
I don't seem to have battery on the microphone. If someone have questions, please put online. We also open for questions in the room. Some questions, please.
I think the battery's fine, actually. Yeah, battery's okay. Well, I've got the microphone now, so I've got one. This was just a ruse for me to get the microphone. So those of us, this is a fantastic talk. I really enjoyed it. I thought it was great. Lovely. Those of us who wasted a lot of our life looking for ore deposits on, on the continents without considering or without having any knowledge of what was going on the margins, spend a lot of time trying to think about repeatedly reactivated crustal block boundaries within the continents that seem to control a lot of major ore deposits, and no doubt in some cases related to ancient subduction zones that we don't understand. And certainly, deposits like Alumbrera, for example, are very systematically related with respect to ancient structures within the South American continent. So my question is, have you, in your analysis, I didn't really see much mention of pre-existing structure within the crust as having any influence whatsoever on the location or nature of the volcanism or deposits. And I was just wondering if that was something that you feel can be discounted in this case, or that you've taken into account and just didn't talk about it.
Yeah, well, clearly the crustal structures play a huge role. So it's really, the kind of reconstructions that I've presented are, the very, very large picture. So, trying to understand the plate boundary at the larger scale, but in the end, the location where you actually got to get, you're going to get an ore deposit depends on how those, fluids and magmas make their way to in the crust. So to your question, I have not considered that because it was never kind of the focus of my research, but clearly, you need to basically link those lithospheric scale structures with crustal scale structures. And when you actually look for ore deposits, you certainly need to understand the crustal architecture.
Any comment about the interaction with the plume? And that's a question from Carlos Spear.
Well, it's, the question that I did not address, maybe because I'm not an economic geologist, and when I get to when I get to think about why actually we get enrichment in metals in these environments, what actually controlling that, I don't know the answer. So the one thing that we do recognize is that the Nazca reed subduction, for example, has the area of Nazca reed subduction is empirically related to ore deposits. Now, the Nazca Ridge was formed by a plume. So, so maybe the answer is yes, that there is a very important relationship to the plume, and that you need to have a plume, you need to create a ridge, like a kind of an oceanic plateau, in order to create, to generate these types of ore deposits. On the other hand, if you think about Peru and Chile, a lot of the very large ore deposits are actually much earlier. So I haven't discussed them because they are older and they are clearly unrelated to the subduction of the Nazca Ridge or the other ridges. And you ask yourself, why is the system, in South America is so rich? I mean, it seems that it's rich anyway. So, perhaps the system is kind of, it's kind of pregnant, it's kind of fertile, and you just need to touch it in order to create an ore deposit. So whether the plume plays a role or not, I don't know.
I think there's a question on the chat rather than the Q&A. This is more of a comment. How do I get to chat?
Okay, I'll get you the chat. Yeah.
Could this anomalous subduction analysis be applied to older fold belts like the Lackland fold belt?
Yes, that's what I would like. I mean, that's my motivation in doing that. So the reason that we went into such details working on Holocene volcanoes in the Andes is mainly because I was interested in whether we can say something more fundamental on, how to go to somewhere in Victoria, New South Wales, looking at a piece of rock and say, something is wrong here. This is not normal, a normal arc. One of the biggest problems is that many of the rocks that we do find in Eastern Australia, for example, are plutonic and not volcanic. And whether you can translate that to a plutonic rocks, whether it's the same that we did here, can be done on diorites and granite, that is not so straightforward. So I think it's a direction to think. It needs more work, but that's the idea. But particularly with volcanic rocks, I think that those criteria do if we do have good exposures of a volcanic arc, these criteria could be applied with caveats, of course, because many of the thresholds that we have used are relevant to the Andes. So perhaps you will need to kind of completely change the thresholds for what you define as anomalous. What is anomalous in the Andes will not necessarily be anomalous in a system that we even saw that in the Andes. Just comparing the southern Andes, the central and the northern Andes, we saw that in some of the criteria, where the southern Andes look completely anomalous, like everything was, not everything, but a lot was anomalous. That obviously does not mean that all those volcanoes are not behaving as they should. It's basically just because the crust is much thinner, you're close to an area of the Chile ridge subduction, the edge of the slab. You need to kind of tailor those criteria for specific regions.
Thank you very much again. Next week, we almost certainly will have an online presentation from Regina. She's from Tech Metals with insights on unlocking future resources through ore body knowledge and geometallurgy. We are in the loop to get some corporate approvals to have her presenting. So in the case she can't join us, we will have a plan B. So please stay tuned with us. Thank you again for Professor Gideon presentation. Please join me to thank you.